A fast-neutron reactor, or simply a fast reactor, is a category of nuclear reactor in which the fission chain reaction is sustained by fast neutrons. Such a reactor needs no neutron moderator, but must use fuel that is relatively rich in fissile material when compared to that required for a thermal reactor. Introduction. Basic fission concepts. In order to sustain a fission chain reaction, the neutrons released in fission events have to react with other atoms in the fuel. The chance of this occurring depends on the energy of the neutron. Most atoms will only undergo induced fission with high-energy neutrons, although a smaller number prefer much lower energies. Natural uranium consists mostly of three isotopes, U-238, U-235, and trace quantities of U-234, a decay product of U-238. U-238 accounts for roughly 99.3% of natural uranium and undergoes fission only by neutrons with energies of 5 MeV or greater, the so-called fast neutrons. About 0.7% of natural uranium is U-235, which undergoes fission by neutrons of any energy, but particularly by lower-energy neutrons. When either of these isotopes undergoes fission, they release neutrons around 1 to 2 MeV, too low to cause fission in U-238, and too high to do so easily in U-235. The common solution to this problem is to slow the neutron from these fast speeds using a neutron moderator. Any substance that reacts with the neutrons and makes them give up some of their energy. The most common moderator is normal water, which slows the neutrons through inelastic scattering until the neutrons reach thermal equilibrium with the water. The key to reactor design is to carefully lay out the fuel and water so the neutrons have time to slow enough to become highly reactive with the U-235, but not so far as to allow them easy pathways to escape the reactor core entirely. Although U-238 will not undergo fission by the neutrons released in fission, thermal neutrons can be captured by the nucleus to transmute the atom into Pu-239. Pu-239 has a neutron cross-section very similar to that of U-235, and most of the atoms created this way will undergo fission from the thermal neutrons. In most reactors this accounts for as much as 1/3 of the energy being generated. Not all of the Pu-239 is burned up during normal operation, and the leftover, along with leftover U-238, can be separated out to be used in new fuel during nuclear reprocessing. Water is a common moderator for practical reasons, but has its disadvantages. From a nuclear standpoint, the primary problem is that water can absorb a neutron and remove it from the reaction. It does this just enough that the amount of U-235 in natural ore is too low to sustain the chain reaction. The neutrons lost their absorption in the water, and U-238, along with those lost to the environment, results in too few left in the fuel. The most common solution to this problem is to slightly concentrate the amount of U-235 in the fuel to produce enriched uranium, with the leftover U-238 known as depleted uranium. Other designs use different moderators, like heavy water, that produce more neutrons than they absorb, allowing them to run on unenriched fuel. In either case, the reactor's neutron economy is based on thermal neutrons. Fast fission breeders. Although U-235 and Pu-239 are less sensitive to higher energy neutrons, they still remain somewhat reactive well into the MeV area. This means that if you enrich the fuel, you will eventually reach a threshold where there are enough fissile atoms in the fuel that a chain reaction can be maintained even with fast neutrons. The primary advantage is that by removing the moderator, the size of the reactor can be greatly reduced, and to some extent the complexity. This is commonly used for shipboard and submarine reactor systems, where size and weight are major concerns. The downside to the fast reaction is that fuel enrichment is an expensive process. so this is generally not suitable for electrical generation or other roles where cost is more important than size. There is another advantage to the fast reaction that has led to considerable development for civilian use. Fast reactors lack a moderator, and thus lack one of the systems that remove neutrons from the system. Those running on Pu-239 further increase the number of neutrons, because its most common fission cycle gives off 3 neutrons rather than the mix of 2 and 3 neutrons released from U-235. By surrounding the reactor core with a moderator and then a blanket of U-238, those neutrons can be captured and used to breed more Pu-239. This is the same reaction that occurs internally in conventional designs. But in this case the blanket does not have to sustain a reaction and thus can be made of natural uranium or even depleted uranium. Due to the surplus of neutrons from Pu-239 fission, the reactor will actually breed more Pu-239 than it consumes. The blanket material can then be processed to extract the Pu-239 to replace the losses in the reactor, and the surplus is then mixed with other fuel to produce MOX fuel that can be fed into conventional slow neutron reactors. A single fast reactor can thereby feed several slow ones, greatly increasing the amount of energy extracted from the natural uranium, from less than 1% in a normal once-through cycle, to as much as 60% in the best fast reactor cycles. Given the limited stores of natural uranium ore, and the rate that nuclear power was expected to take over baseload generation, through the 1960s and 70s fast breeder reactors were seen as the solution to the world's energy needs. Using twice-through processing, a fast breeder economy increases the fuel capacity of known ore deposits by as much as 100 times, meaning that even existing ore sources would last hundreds of years. The disadvantage to this approach is that the breeder reactor has to be fed highly enriched fuel, which is very expensive to produce. Even though it breeds more fuel than it consumes, the resulting MOX is still expensive. It was widely expected that this would still be below the price of enriched uranium as demand increased and known resources dwindled. Through the 1970s, breeded designs were being widely experimented on, especially in the USA, France and the USSR. However, this coincided with a crash in uranium prices. The expected increased demand led mining companies to build up new supply channels, which came online just as the rate of reactor construction stalled in the mid-1970s. The resulting oversupply caused fuel prices to decline from about $40 in 1980 to less than $20 by 1984. Breeders produce fuel that was much more expensive, on the order of $100 to $160. And the few units that had reached commercial operation proved to be economically disastrous. Interest in breeder reactors were further muted by Jimmy Carter's April 1977 decision to defer construction of breeders in the U.S. due to proliferation concerns, and the terrible operating record of France's Superphénix reactor. Advantages: fast-neutron reactors can reduce the total radiotoxicity of nuclear waste, and dramatically reduce the waste's lifetime. They can also use all or almost all of the fuel in the waste. Fast neutrons have an advantage in the transmutation of nuclear waste. With fast neutrons, the ratio between splitting and the capture of neutrons of plutonium or minor actinide is often larger than when the neutrons are slower, at thermal or near-thermal, epithermal speeds. The transmuted odd-numbered actinides split more easily. After they split, the actinides become a pair of fission products. These elements have less total radiotoxicity, since disposal of the fission product is dominated by the most radiotoxic fission product, cesium-137, which has a half-life of 30.1 years. The result is to reduce nuclear waste lifetimes from tens of millennia to a few centuries. The processes are not perfect, but the remaining transuranics are reduced from a significant problem to a tiny percentage of the total waste. Because most transuranics can be used as fuel, fast reactors technically solve the fuel shortage argument against uranium-fueled reactors without assuming unexplored reserves, or extraction from dilute sources such as ordinary granite or the ocean. They permit nuclear fuels to be bred from almost all the actinides, including known, abundant sources of depleted uranium and thorium, and light water reactor wastes. On average, more neutrons per fission are produced from fissions caused by fast neutrons than from those caused by thermal neutrons. This results in a larger surplus of neutrons beyond those required to sustain the chain reaction. These neutrons can be used to produce extra fuel, or to transmute long half-life waste to less troublesome isotopes, such as was done at the PHE-Acute-NIX reactor in Marcoule in France, or some can be used for each purpose. Though conventional thermal reactors also produce excess neutrons, fast reactors can produce enough of them to breed more fuel than they consume. Such designs are known as fast breeder reactors. The fast reactor doesn't just transmute the inconvenient even-numbered transuranic elements. It transmutes them, and then fissions them for power, so that these former wastes would actually become valuable. Disadvantages: breeder reactors are costly to build and operate, and are not likely to be cost-competitive with thermal reactors unless the price of uranium increases dramatically. Due to the low cross-sections of most materials at high neutron energies, critical mass in a fast reactor is much higher than a thermal reactor. In practice, this means significantly higher enrichment, greater than 20% enrichment in a fast reactor compared to less than 5% enrichment in typical thermal reactors. This raises greater nuclear proliferation and nuclear security issues. Sodium is often used as a coolant in fast reactors, because it does not moderate neutron speeds much and has a high heat capacity. However, it burns and foams in air. It has caused difficulties in reactors, although some sodium-cooled fast reactors have operated safely. Since liquid metals have low moderating power and ratio and no other moderator is present, the primary interaction of neutrons with liquid metal coolants is the reaction, which induces radioactivity in the coolant. Boiling in the coolant, e.g., in an accident, would reduce coolant density and thus the absorption rate, such that the reactor has a positive void coefficient, which is dangerous and undesirable from a safety and accident standpoint. This can be avoided with a gas-cooled reactor, since voids do not form in such a reactor during an accident. However, activation in the coolant remains a problem. A helium-cooled reactor would avoid this, since the elastic scattering and total cross-sections are approximately equal, i.e., there are very few reactions in the coolant, and the low density of helium at typical operating conditions means that the amount neutrons have few interactions with coolant. Nuclear reactor design. Coolant water, the most common coolant in thermal reactors, is generally not a feasible coolant for a fast reactor, because it acts as a neutron moderator. However, the generation IV reactor known as the supercritical water reactor with decreased coolant density may reach a hard enough neutron spectrum to be considered a fast reactor. Breeding, which is the primary advantage of fast over thermal reactors, may be accomplished with a thermal, light water-cooled and moderated system using very high enriched uranium. All current fast reactors are liquid metal-cooled reactors. The early Clementine reactor used mercury coolant and plutonium metal fuel. Sodium-potassium alloy coolant is popular in test reactors due to its low melting point. In addition to its toxicity to humans, mercury has a high cross-section for the reaction, causing activation in the coolant and losing neutrons that could otherwise be absorbed in the fuel, which is why it is no longer used or considered as a coolant in reactors. Molten lead cooling has been used in naval propulsion units as well as some other prototype reactors. All large-scale fast reactors have used molten sodium coolant. Another proposed fast reactor is a molten salt reactor, one in which the molten salt's moderating properties are insignificant. This is typically achieved by replacing the light metal fluorides in the salt carrier with heavier metal chlorides. Gas-cooled fast reactors have been the subject of research as well, as helium, the most commonly proposed coolant in such a reactor, has small absorption and scattering cross-sections, thus preserving the fast neutron spectrum without significant neutron absorption in the coolant. Nuclear fuel in practice, sustaining a fission chain reaction with fast neutrons means using relatively highly enriched uranium or plutonium. The reason for this is that fissile reactions are favored at thermal energies. Since the ratio between the Pu-239 fission cross-section and U-238 absorption cross-section is ~100 in a thermal spectrum and 8 in a fast spectrum, fission and absorption cross-sections are low for both Pu-239 and U-238 at high energies, which means that fast neutrons are likelier to pass through fuel without interacting than thermal neutrons, thus more fissile material is needed. Therefore it is impossible to build a fast reactor using only natural uranium fuel. However, it is possible to build a fast reactor that will breed fuel by producing more fissile material than it consumes. After the initial fuel charge, such a reactor can be refueled by reprocessing. Fission products can be replaced by adding natural or even depleted uranium with no further enrichment required. This is the concept of the fast breeder reactor or FBR. So far, most fast neutron reactors have used either MOX or metal alloy fuel. Soviet fast neutron reactors have been using uranium fuel. The Indian prototype reactor has been using uranium carbide fuel, while criticality at fast energies may be achieved with uranium enriched to 5.5 weight% uranium-235. Fast reactor designs have often been proposed with enrichments in the range of 20% for a variety of reasons, including core lifetime. If a fast reactor were loaded with the minimal critical mass, then the reactor would become subcritical after the first fission had occurred. Rather, an excess of fuel is inserted with reactivity control mechanisms, such that the reactivity control is inserted fully at the beginning of life to bring the reactor from supercritical to critical. As the fuel is depleted, the reactivity control is withdrawn to mitigate the negative reactivity feedback from fuel depletion and fission product poisons. In a fast breeder reactor, the above applies, though the reactivity from fuel depletion is also compensated by the breeding of either uranium-233 or plutonium-239 and 241 from thorium-232 or uranium-238, respectively. Control. Like thermal reactors, fast neutron reactors are controlled by keeping the criticality of the reactor reliant on delayed neutrons, with gross control from neutron-absorbing control rods or blades. They cannot, however, rely on changes to their moderators because there is no moderator. So Doppler broadening in the moderator, which affects thermal neutrons, does not work, nor does a negative void coefficient of the moderator. Both techniques are very common in ordinary light water reactors. Doppler broadening from the molecular motion of the fuel, from its heat, can provide rapid negative feedback. The molecular movement of the fissionables themselves can tune the fuel's relative speed away from the optimal neutron speed. Thermal expansion of the fuel itself can also provide quick negative feedback. Small reactors such as those used in submarines may use Doppler broadening or thermal expansion of neutron reflectors. History. A 2008 IAEA proposal for a fast reactor knowledge preservation system notes that, during the past 15 years there has been stagnation in the development of fast reactors in the industrialized countries that were involved, earlier, in intensive development of this area. All studies on fast reactors have been stopped in countries such as Germany, Italy, the United Kingdom and the United States of America, and the only work being carried out is related to the decommissioning of fast reactors. Many specialists who were involved in the studies and development work in this area in these countries have already retired or are close to retirement. In countries such as France, Japan and the Russian Federation that are still actively pursuing the evolution of fast reactor technology, the situation is aggravated by the lack of young scientists and engineers moving into this branch of nuclear power.